When sizing conductors and overcurrent protection for continuous loads, it's important to understand the requirements outlined in the National Electrical Code, specifically Section 110.14. C1. This section addresses conductor temperature limitations and the proper selection of equipment. For continuous loads, the overcurrent protective device, or OCT, shall not be less than the marked rating of the load. Let's consider a scenario where we have a small processing machine with a nameplate current rating of 38 amps, and this load is considered continuous. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. According to the provided answer, number 8 THWN copper conductors and a 50 amp breaker would be suitable for this application. Let's analyze why this is the case. Firstly, we need to determine the ampacity of the number 8 THWN copper conductors. According to the NEC ampacity tables, number 8 THWN copper conductors with a 75 degrees Celsius insulation rating are typically rated for 40 amps in a raceway or cable. This means that the conductors can safely carry up to 40 amps of current without exceeding their temperature rating. Secondly, let's examine the selection of the 50 amp breaker. NEC Section 110.14. C1 states that for continuous loads, the overcurrent protection device shall not be less than 125% of the continuous load. In other words, we need to multiply the continuous load by 1.25 to determine the minimum allowable size of the overcurrent protection device. In this case, 38 amps multiplied by 1.25 equals 47.5 amps. Since standard size breakers are available in 5 amp increments, the next highest standard size breaker is 50 amps. Therefore, a 50 amp breaker would be suitable for this application, as it provides adequate protection for the circuit while allowing the continuous load to operate without nuisance tripping. It is important to note that the overcurrent protection device should protect the conductors from overcurrent conditions such as short circuits and ground faults, while also allowing the normal operating current of the load to flow without interruption. Now, let's consider a scenario where fuses are used instead of a breaker to protect the circuit. In this case, the selection of the fuse size would be slightly different. According to the NEC, fuses are typically rated at their full ampacity, meaning that a 38 amp fuse would be required to protect a 38 amp continuous load. This is because fuses do not have a continuous current rating like breakers do. A breaker is designed and tested to carry 80% of its rated current continuously, whereas a fuse is expected to carry 100% of its rated current and open above 100%. Therefore, if the circuit were to be protected by fuses, a 38 amp fuse would be required to meet the requirements of NEC Section 110.14. Seat 1. In summary, both the number 8 THWN copper conductors and the 50 amp breaker meet the requirements of NEC Section 110.14. C1 for a continuous load with a nameplate current rating of 38 amps. However, if the circuit were to be protected by fuses, a 38 amp fuse would be required. Let's delve deeper into the factors that influence conductor sizing and overcurrent protection. Firstly, the ambient temperature plays a significant role in determining the ampacity of conductors. The ampacity tables in NEC are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than 30 degrees Celsius, the ampacity of the conductors must be dilated to account for the increased heat. Dilating factors are provided in the NEC tables 310.15. These factors specify the percentage reduction in ampacity for various temperature ranges. For example, if the ambient temperature is 40 degrees Celsius, the ampacity of the number 8 THWN copper conductors may need to be reduced by 8%. Secondly, the number of current-carrying conductors in a raceway or cable also affects the ampacity of the conductors. When multiple current-carrying conductors are installed in close proximity, the heat generated by each conductor can raise the overall temperature within the raceway or cable. This can reduce the ampacity of the conductors. Correction factors are provided in NEC Table 310.15. B3. Etercan for the number of current carrying conductors in a raceway or cable. For example, if there are 4 to 6 current carrying conductors in a raceway, the ampacity of the conductors must be derated to 80% of their original ampacity. Thirdly, the termination temperature rating of the equipment must also be considered when sizing conductors. Electrical equipment, such as breakers, switches, and receptacles, are typically marked with a termination temperature rating. This rating indicates the maximum temperature that the equipment terminals can withstand without being damaged. The conductors connected to the equipment must have an ampacity that is equal to or greater than the termination temperature rating of the equipment. For example, if a breaker is marked with a 75°C termination temperature rating, the conductors connected to the breaker must have an ampacity that is equal to or greater than the 75°C ampacity of the conductors. In some cases, the termination temperature rating of the equipment may be lower than the ampacity of the conductors. In these cases, the conductors must be sized based on the lower of the two values. For example, if a breaker is marked with a 60°C termination temperature rating and the number 8 THWN copper conductors have a 75°C ampacity of 40 amps, the conductors must be sized based on the 60°C ampacity of the conductors, which may be lower than 40 amps. It is important to carefully consider all of these factors when sizing conductors and overcurrent protection for electrical circuits. Failure to do so can result in overheating of the conductors, damage to the equipment, and even fire. Now let's explore the different types of overcurrent protection devices that are available. The two main types of overcurrent protection devices are breakers and fuses. Breakers are electromechanical devices that are designed to automatically open a circuit when an overcurrent condition occurs. Breakers are resettable, meaning that they can be reset after they have tripped. Fuses are one-time devices that are designed to melt and open a circuit when an overcurrent condition occurs. Fuses must be replaced after they have blown. There are several different types of breakers available, including thermal magnetic breakers, electronic trip breakers, and instantaneous trip breakers. Thermal magnetic breakers are the most common type of breaker. They use a bimetallic strip and an electromagnet to detect overcurrent conditions. The bimetallic strip bends when it is heated by an overcurrent, causing the breaker to trip. The electromagnet trips the breaker instantly when a short circuit occurs. Electronic trip breakers use electronic circuitry to detect overcurrent conditions. They offer more precise and adjustable tripping characteristics than thermal magnetic breakers. Instantaneous trip breakers are designed to trip instantly when a short circuit occurs. They do not provide overload protection. There are also several different types of fuses available, including cartridge fuses, plug fuses, and blade fuses. Cartridge fuses are cylindrical fuses that are typically used in industrial and commercial applications. Plug fuses are screw-in fuses that are typically used in residential applications. Blade fuses are flat fuses that are typically used in automotive applications. When selecting an overcurrent protection device, it is important to consider the application, the load characteristics, and the available fault current. The application will determine the type of overcurrent protection device that is required. For example, a residential application may require the use of plug fuses, while an industrial application may require the use of cartridge fuses. The load characteristics will determine the size and type of overcurrent protection device that is required. For example, a motor load may require the use of a time delay fuse or a motor circuit protector. The available fault current will determine the interrupting rating of the overcurrent protection device that is required. The interrupting rating is the maximum amount of fault current that the overcurrent protection device can safely interrupt. It is important to select an overcurrent protection device with an interrupting rating that is greater than or equal to the available fault current at the point of installation. In addition to NEC Section 110.14 C1, there are several other NEC sections that are relevant to conductor sizing and overcurrent protection. These sections include NEC Section 240.4, which covers the protection of conductors, NEC section 310.15, which covers the ampacity of conductors, and NEC section 430, which covers motor circuits. It is important to consult these NEC sections when sizing conductors and overcurrent protection for electrical circuits. Furthermore, it's essential to understand the concept of conductor dirting and correction factors as previously mentioned. These adjustments are crucial for ensuring the safe operation of electrical systems, especially in environments with high ambient temperatures or where multiple conductors are bundled together. The NEC provides detailed tables and guidelines for calculating these dirting and correction factors, which must be applied diligently to prevent conductor overheating and potential hazards. Let's revisit the example of the 38 amp continuous load and consider the impact of ambient temperature. If the equipment is located in an area where the ambient temperature regularly exceeds 30 degrees Celsius, the ampacity of the number 8 THWN copper conductors will need to be derated. Using the NEC tables, we can determine the appropriate dirting factor for the specific temperature range. For instance, if the ambient temperature is 40 degrees Celsius, the dirting factor might be 0.91. This means that the ampacity of the number 8 THWN conductors would be reduced to 40 amps multiplied by 0.91, which equals 36.4 amps. In this case, the number 8 THWN conductors would no longer be suitable for the 38 amp continuous load, and a larger conductor size would be required. Similarly, if the number of current carrying conductors in a raceway exceeds 3, a correction factor must be applied to the conductor ampacity. The NEC provides correction factors based on the number of conductors. For example, if there are 4 to 6 current carrying conductors in a raceway, the correction factor might be 0.8. This means that the ampacity of the number 8 THWN conductors would be reduced to 40 amps multiplied by 0.8, which equals 32 amps. Again, in this scenario, the number 8 THWN conductors would not be adequate for the 38 amp continuous load, and a larger conductor size would be necessary. The selection of the overcurrent protection device is also influenced by the type of load being served. For motor loads, the NEC requires the use of specific motor circuit protection devices such as inverse time circuit breakers or time delay fuses. These devices are designed to accommodate the high inrush current that occurs when a motor starts, while still providing overload and short circuit protection. The sizing of motor circuit protection devices is based on the motor's full load current rating and the motor's code letter, which indicates the motor's inrush current characteristics. The NEC provides detailed tables and guidelines for sizing motor circuit protection devices, which must be followed carefully to ensure proper protection of the motor and the circuit. Furthermore, the available fault current at the point of installation is a critical factor in selecting the appropriate overcurrent protection device. The available fault current is the maximum amount of current that could flow in the event of a short circuit. The overcurrent protection device must have an interrupting rating that is equal to or greater than the available fault current. If the interrupting rating of the overcurrent protection device is less than the available fault current, the device could fail to interrupt the fault current, which could result in equipment damage, fire, or injury. Electrical engineers typically conduct fault current studies to determine the available fault current at various points in an electrical system. These studies take into account the impedance of the electrical system components, such as transformers, conductors, and protective devices. The results of the fault current study are used to select overcurrent protection devices with adequate interrupting ratings. In addition to the NEC requirements, there may be local codes and regulations that apply to conductor sizing and overcurrent protection. It is important to consult with the local electrical inspector to ensure that all applicable codes and regulations are followed. Electrical work should only be performed by qualified and licensed electricians who are familiar with the NEC and local codes. Improperly installed electrical systems can be dangerous and can result in serious injury or death. In conclusion, sizing conductors and overcurrent protection for continuous loads requires a thorough understanding of the NEC requirements, conductor dirting and correction factors, load characteristics, available fault current, and local codes. By carefully considering all of these factors, electrical professionals can ensure the safe and reliable operation of electrical systems. To further illustrate the practical application of these concepts, let's consider another example. Suppose we have a heating element with a nameplate current rating of 20 amps and it is considered a continuous load. The heating element is installed in an area with an ambient temperature of 35 degrees Celsius, and there are 3 current-carrying conductors in the raceway. Firstly, we need to determine the minimum allowable ampacity of the conductors. Since the load is continuous, we must multiply the nameplate current rating by 1.25, which gives us 25 amps. This means that the conductors must have an ampacity of at least 25 amps. Secondly, we need to apply the appropriate dirting and correction factors. According to the NEC tables, the dirting factor for an ambient temperature of 35 degrees Celsius is 0.96, and the correction factor for 3 current-carrying conductors in a raceway is 1.0. Therefore, the adjusted ampacity of the conductors is equal to the original ampacity multiplied by 0.96 and 1.0. Thirdly, we need to select a conductor size that has an adjusted ampacity of at least 25 amps. According to the NEC ampacity tables, number 12 THWN copper conductors have an ampacity of 30 amps at 30 degrees Celsius. Applying the dirting factor of 0.96, the adjusted ampacity of the number 12 THWN conductors is 28.8 amps, which is greater than the minimum required ampacity of 25 amps. Therefore, number 12 THWN copper conductors would be suitable for this application. Fourthly, we need to select an overcurrent protection device that is rated at not more than the ampacity of the conductors. In this case, the number 12 THWN conductors have an ampacity of 28.8 amps after dirty. Therefore, we can select a 25 amp breaker or fuse to protect the circuit. It is important to note that the overcurrent protection device should protect the conductors from overcurrent conditions while also allowing the normal operating current of the load to flow without interruption. In this example, a 25 amp breaker or fuse would provide adequate protection for the circuit while allowing the 20 amp heating element to operate without nuisance tripping. By following these steps, electrical professionals can ensure that conductors and overcurrent protection devices are properly sized for continuous loads, taking into account ambient temperature, number of conductors, and other relevant factors. This will help to prevent overheating of the conductors, damage to the equipment, and potential fire hazards. In addition to the technical aspects of conductor sizing and overcurrent protection, it is also important to consider the safety aspects of electrical work. Electrical work should only be performed by qualified and licensed electricians who are familiar with the NEC and local codes. Before starting any electrical work, it is important to energize the circuit and verify that it is energized using a voltage tester. Personal protective equipment, such as safety glasses, gloves, and insulated tools, should be worn at all times when working on electrical circuits. When working on energized circuits, it is important to use extreme caution and to follow all safety procedures. Avoid working alone, and always have someone nearby who can assist in case of an emergency. By following these safety precautions, electrical professionals can minimize the risk of electrical shock, burns, and other injuries. In conclusion, conductor sizing and overcurrent protection are critical aspects of electrical system design and installation. A thorough understanding of the NEC requirements, conductor dirting and correction factors, load characteristics, available fault current, local codes, and safety precautions is essential for ensuring the safe and reliable operation of electrical systems.